today's webinar. My name is Matt Novak. I'm here with Bruker, and I appreciate you taking time today to spend time learning about a clearer look at engineered surfaces. We have an exciting webinar today, and I'm looking forward to sharing this time with you. First, I'll introduce a little bit about Bruker for those of you who don't know Bruker. Then I'm actually going to have the pleasure of doing a very nice introduction of a brand new product that we have here from Bruker in Tucson, Arizona, called the Contour Elite. I'm very excited to show you some of those capabilities about how metrology can be done with a 3D optical microscope, but also can be combined with very nice features for ease of use, imaging, and enhanced imaging, particularly for some different application examples I'll show. But before I begin the detailed webinar, I would like to just mention there will be at the end of the presentation. Today's presentation is relatively short, probably 30 minutes is enough. Then there will be some time for questions and answers at the end. And if you, while we go through the presentation, type your questions into the question dialog, I can make sure to answer those at the end of the discussion. I'd also like, if you could please take probably 30 seconds more when you leave the webinar to answer some questions in a survey that lets us know how to improve the content of these webinars for people who are viewing them, so that we can deliver things of value and of interest to you that relate to the products that we deliver. So without further ado, I'll go ahead and begin. As I said, my name is Matt Novak. I'm the Director of Technology and Applications here in the Stylus and Optical Metrology business unit for Bruker. I've been with the team here a little over 4 years. I've got nearly almost 19, I guess 18 or 19 years experience in optical engineering, fabrication, and metrology. And I earned my PhD while working in a private sector metrology equipment, delivering instrument design, assembly, and test, which makes for a very fun work here in the Bruker environment. Bruker itself, just a very quick overview, is a founded in 1960 company. It's nearly a $1.8 billion in revenue, 6,700 employees, and about 1,000 R&D professionals. We here in Bruker Stylus and Optical Metrology are under the Bruker Nano Group, which is over here, third column over. Just some interesting facts. We are a global organization. We have 82% of our revenues are outside of the US, and we do have direct sales in over 33 countries now. A little bit about that B Nano group, and which starts tying into what the topic of the webinar today is about, having a clear look at engineered surfaces and how I'll introduce the Contour Elite. We do serve a wide range of application spaces and markets across industry and research. There are material science and life science applications. We look at materials research for metals and ceramics, polymers, composites, different finishing techniques and capabilities. We have users using our equipment to measure medical materials, looking at pharmaceuticals, different coatings, coatings and capabilities for both function and performance of the products are measured with our products as well. And we also have users in green technology and heavy industry. So there's a wide range of applications that are served by the equipment from our businesses. And today I'm going to spend some time showing you some specific capabilities on a new product that's meant to give a good, clear look at some of these types of surfaces. Bruker Nano Surfaces Division, which is the group where I work and belong, actually has been a combination of a few different capabilities and businesses over the last several years. We have excellence in microscopy, both fluorescence microscopy, 3D optical microscopy, which is more the topic today, atomic force or scanning probe microscopes, as well as Stylus profilometry and tribology and mechanical testing. We pride ourselves in delivering the highest performance across these types of platforms and working to be a world leader in the scientific and industrial instrumentation innovation. So we keep working towards excellence in the introduction of new products and technologies for our users as time goes by. A brief word about the Stylus and Optical Metrology business unit. We have a group here in Tucson, Arizona. It's a part of Bruker Nano, as I mentioned, and the Bruker Nano Surfaces division, where we again focus on technology leadership for our particular capabilities, traditionally 3D optical microscopes and Stylus profilometry. We have a group that is dedicated to product innovation and development and doing technology leadership in these areas, including a group of awards, 60 patents and multiple patents pending, 4 R&D 100 awards and 6 Photonics Circle of Excellence awards. But in addition to this, we pride ourselves on our manufacturing excellence. The team here in Arizona works from Lean Six Sigma based processes. They're able to do quite a rapid production ramp, and the entire operation employs ISO 9000 compliant practices, which is important for instrumentation delivered into a range of industries. So for the main portion of the discussion, I'm going to introduce a brand new product that we have. It's called the Contour Elite. And as part of that introduction, I'm going to make a brief review of 3D optical microscope characteristics and capabilities, which are traditionally used for surface metrology for engineered surfaces. And then for the remainder of the webinar, I'm going to discuss how the Contour Elite, this new product with its capabilities, can help users to see more clearly the details of the surfaces of interest and understand more about the samples that they need to measure and to quantify and to present results. So for those of you who may not know, Bruker has specialized in making very high accuracy 3D optical microscopes based on white light interference as the core technology. Basically, what this chart shows is a schematic that has the source, illumination source, some distribution optics that send the light through a special objective that focuses the light onto the sample of interest. And this objective functions as a way of making special images that can detail the height through phase. So this special objective is scanned on an accurate scanner, and a CCD camera captures the intensity images that are made while scanning through focus to enable the computation of a height map. And that can be done in a couple of different ways. There are actually several different ways, but typically for this type of an interference system, you can compute the height based on the phase if the sample is very smooth, or you might just compute the center of mass of the focus signals across the camera if it is a more rough or diffuse sample. So I said a lot of things in words there, but I think a picture can illustrate very well what I mean by this kind of a 3D optical scan. And what you see here on this image is a sample. This is meant to be a step height. So you're looking down from the top over here on the live view, and you can see the sample step. And this side is higher, this side is lower. And when I proceed with this graphic, you'll see the instrument, the schematic of the microscope that I just mentioned, scanning through focus, and the images collected and then producing a height map. So those are the interference fringes I talked about, and those intensity frames are being captured now on the CCD, and then automatically a height mapping algorithm is used to compute the best focus pixels in this case. And here you see a nice 3D image of the surface. You can note traditionally the heights are mapped in a pseudo color, red is high, blue is low. And that's important to keep in mind as we go forward and discuss how the new Contour Elite capabilities can present and show new information for samples to the users. Traditional images look a lot like this. This example is a large area, relatively large area, maybe 10 millimeters long or 20 millimeters long, stitched over a corroded surface to get a height map encoded, as I mentioned, via color. Red is high, blue is low. So here are some corrosion pits, and the red area is just the substrate. You can also view the sample as a grayscale, looking at a zoomed in view here of that same area, but showing this as grayscale to make it look as like an SEM might, for example. And you can see the range is again encoded via that false color. And this is a traditional way of presenting data for this kind of a 3D microscope. And what are the benefits? The beauty of this kind of a technology is that it has very high precision in the vertical axis. So while you scan, no matter what field of view and objective you are using, the vertical resolution is dictated by the wavelength of light and the numerical aperture, and also the interference that you make. You can compute the centers of mass to roughly about a 3 nanometer precision for the surface, and you can also do for smooth surfaces down below 1 nanometer for precision, and that's independent of the magnification you use. You can see larger area, 5x or 2.5x or even 1x fields of view, which can be 10 millimeters or more on a side, up to a 50 or 100x objective, which might get you an image down to as small as 25 by 25 micron square. All of those fields of view can be measured quickly with accuracy, repeatably and reproducibly. And so that's what I mean by fast, accurate GR&R capable configurations. This kind of a technology delivers that across a range of applications that you might see here, something like electronics, functional surface metrology, where you look at traces or steps, or even just frictional surfaces, bearing surfaces, how they work together. You can look at MEMS or orthopedics, many different application spaces. The method is non-contact and non-destructive, and offers, with the kind of software that we use to control our systems, which is called Vision, we offer hundreds of analyses, including surface texture analyses according to ISO filtering standards and ISO norms. All of these things give stable operator-independent data, which allow for good control and measurement of engineered surfaces. But you notice in all cases for these traditional types of images, the heights are encoded in the color map that I mentioned before. But what if somebody wants to look at the surface in more detail with better accuracy of the true representation of the surface? And this is where I get a chance to introduce a brand new product called the Contour Elite. This was announced yesterday via press release. And what we're providing here really is trusted metrology, all those same metrology capabilities that I just mentioned for our traditional 3D microscopes, but combining that with high-fidelity images for clearest results. And for the remaining portion of the webinar, I'm going to show you a little bit of what I mean by that for the Contour Elite. So what's new inside the Contour Elite? It's still a 3D microscope. It looks similar, it has similar body style, and it has the same types of objectives available across a family of tools. The Contour Elite family has tabletop and freestanding models that are available. But what we've done is we've developed some proprietary algorithms, data display, software enhancements, to improve both specular and diffuse imaging from a variety of surfaces. We've also developed some enhanced illumination capability to combine with further proprietary software that enables a really great look at quite a range of samples. So there's, again, the key thing to remember here is that we have all the capabilities of the 3D optical microscopes that Bruker has delivered for trusted metrology, but now we are providing high fidelity images for clearest results. So I'm going to give some examples of what that means. You remember the graphic that showed the 3D view on the step sample that I just did a few moments ago. This is the same type of a view through a traditional 3D interference microscope that you would normally have, and a corresponding height map that would be encoded as before. Somebody might be curious about what you really see in the live video, and having these elite capabilities for this kind of a PCB sample, a type of engineered surface, really can deliver value. You can see a lot more clearly when you have the elite capability what's happening on the surface. It enables ease of navigation on your sample, and it also enables a very nice, crisp, through focus image to be displayed and overlaid on top of the height, rather than just encoding the height in a pseudo color. Now you can have, for a grayscale camera just like this, an intensity shaded and overlaid image that corresponds to what you really see on the sample surface. A similar example here, you have a polycrystalline silicon photovoltaic cell, and you can see a height map. There's a reasonable view of what's happening on there, but again, with the elite capabilities, you can bring out a lot of the new nuances and texture of the surface in greater detail, and then make the same kind of a height measurement with that true image overlay onto the three-dimensional data that you would typically do with a pseudo color overlay. This allows the user, if it's a failure analysis person or an engineer on a quality assurance line, looking at images and tracking heights and data, these images can be saved and examined later for failures. For example, if this is a defect, you can see a nice clear picture of that defect and some of these texture changes which weren't available in a traditional kind of imaging on a 3D optical microscope based on interference, but can be delivered now very easily on the Contour Elite with these new capabilities. Here are some further examples. I'm focusing now on some of the top views, just being able to navigate differently. This is a contour plot of a piece of a paper, imaging from top down, and you can see some texture there, and you get a hint of that texture, but with the Contour Elite and the enhanced illumination, you can really bring out a lot of the details that are missing from the traditional view because of the type of optics that are present in an interference microscope. We've done the work to overcome a lot of those limitations and deliver very nice high-quality microscope images in addition to the high-quality metrology data. And that's really the key for someone who's interested in both the metrology of the functional surfaces or engineered surfaces, but also the details of what is present on the surface and for presenting the findings. Here's an example I really like. I think this illustrates very clearly. This is just for example, a diffuse fossilized fish, and this might not be called an engineered surface, but it's a hardened material. And when I say diffuse, the sample itself is diffuse, as I showed earlier, how diffuse light scatters from a surface. It's not very easy to see any of the details here without the type of illumination enhancements we've done. And you can still see the traditional height encoded as you would, but having those enhanced illumination capabilities really does open up the ability to see clear details, and even in color as an option. Now we are able to display these kinds of images on the Contour Elite. And that's a really exciting new change for our products, and we look forward to the capability being available for our users now. This is another good sample where the difference between the elite functionality and traditional functionality is fairly dramatic. This is an accurate height map of a fibrous paper. You can see the scale is around 50 microns. You can see some details of fibers in the contour plot. And this is a 3D plot with just the fibrous view of the overlay. But if you look at the elite enhanced version of that image with the enhanced illumination and the capabilities for drawing out the color, you get a feel for what's really present on the sample. These are the identical sample, but now you're actually getting not only the trusted metrology result to show the surface texture, but now you get the clearest result showing what's really present on the sample. I also wanted to show this capability is also of benefit even at higher magnifications. You can see here a 2D plot, a contour plot at around a 50x magnification showing some bumps here. And these are, you can see a hint of the details of these pads on the side and the bumps themselves. But when you look at it in the 3D overlay with the overlaid enhanced image, this is really giving the user a lot more information about what's happening on the sample. And I'm really excited for that kind of capability for our systems. Just a brief note, as I mentioned, color images are an optional functionality now. These are something that we're also offering the capability to analyze these in real time to segment based on color. You can segment out the red, for example, here, and then look at the height and show the texture and the height alone after pulling those data only. This is very useful for someone looking to tell the difference between information where there isn't a height difference, but only a color or a corrosion difference, for example. And this is a nice feature that we've added in the Contour Elite suite as well. One of the last things I want to talk about now is that we also have, in addition to these enhanced imaging capabilities and functionalities, we've taken the traditional 3D optical microscope based on interferometry, which for many years was sold as an interferometer. This was an interferometric profiler or an interference-based scientific instrument which needed to be explained from the details of the physics of the interferometry. And that's still important. However, what we've really strived to do with the Contour Elite is to bring this capability of the high technology of interferometry and the high resolution and high accuracy data that it can provide, but also bridge the gap to the ease of use and improved user workflow that many people already expect from a laser scanning microscope or other types of microscopes. So this is one example of another measurement feature that we've implemented. It's a quick measurement feature to improve the ease of use. And what you see here is a through focus image that we've made. Basically, this is easy as 1, 2, 3. You start the measurement setup, you scan and focus on the top of the area of interest, and then you can scan and focus on the bottom of the area of interest, and then just click measure. And the system will automatically compute the range that is needed for the scan and go ahead and make the scan and build this through focus image for the user. And that's a very new and unique capability for an interferometric microscope that we've brought to the market with the Contour Elite. Just as an example to show what I mean, I've made a very brief video that is looking at a small portion of this coin. This is a £1 coin, and I just zoomed in on one of the dragon claws here, and I'm looking at this on just a traditional monochrome camera, but I'd like you to see just how easy it is to make do this build-up image and some of the other unique capabilities that are brought out in the Contour Elite. So right now what you see is a height map that can be built up through focusing on the top surface of one of those dragon claws, and you can see the height. You can also see the depth of focus image being built up in real time as well. And what normally would happen is you could use this feature to let yourself see exactly when you finished a scan, or also build the through focus data. Now I'm showing the height map again to see whether we've scanned the bottom. You can see it coming into focus here. And now we've got a nice overlay that comes out of that whole 3D view. And this is brand new capability for an interference microscope. The Contour Elite is really going to be a different type of a capability for people who are used to traditional interferometric optical profilers. And as I mentioned, this was going to be a little bit of a brief overview of the Contour Elite. So I've come to the end of the 30 minutes, and it's time for a summary and questions. So I'm going to, with that, go ahead and say thank you for taking time to participate today. And I am going to open up the questions dialog so that I can go ahead and answer those for us as we go forward. So someone asked, the first question is, does this technology work with thin films 50 to 100 nanometers? So that's a good question. We do have the capability. We've measured down, personally I've measured down to an 85 nanometer thin film. We have that as an optional package on the systems. The materials that we've looked at so far, basically oxides and nitrides on silicon, but we're open to exploring other film samples as well to see how the system does with those types of materials. Another question, how does this change the vertical resolution of the measurements? So again, the Contour Elite, really the way we're looking at this is trusted metrology, high fidelity imaging, and the clearest results. And the trusted metrology is really about having the same vertical resolution that you have from our 3D optical microscopes that we've delivered into the marketplace, and still having the same technology and capabilities for doing the data analyses and the types of measurements that people need for their metrology problems, but combining that with this new capability for imaging and looking at these types of surfaces in greater detail. So the influence on the vertical resolution is none. There is a direct carryover from the traditional 3D optical microscopes from Bruker and the technology there to the Contour Elite and the technology that it delivers. Another question is about measurement time. Does this add measurement time? So the answer is it depends. I think that's the safest answer. It depends. If a system, the Contour Elite, can be outfitted with both grayscale camera, can be of a standard resolution or a 1K by 1300 higher resolution camera. It can also be outfitted with a color camera of similar resolutions, a standard 640 by 480 or a 1400 by 1000 higher resolution camera, I believe. And so if you have small scans and a small array, the memory requirements are not very high, and the speed is not changed or affected in 1 bit. When you do choose a higher resolution camera and have a much longer scan length, the frames data become more memory intensive, and so then some of the scans can take longer to build up the nice through focus images that I talked about and giving the continuous image. So again, the measurement time, it depends, is really the real answer. But for most cases, if the scan lengths are of 10 to 20 to 50 microns, which is typical for a wide range of applications and samples, and the resolution requirements are not very high, then excuse me, the time requirements are no different than the traditional microscopes that people are used to using. Our microscopes still enjoy the benefit of being fastest for a wide area and longer scan range with the highest resolution, and that's still true of the Contour Elite. Another question, for sandblasting glass or erosion tests where micro cracks and material removal is expected, what information can this technology provide? That's an interesting question. So there are erosion or type surface conditioning tests where we use the equipment to help people make a before and after image. You can fiducialize the before and after images and look at wear volume. You can look at some of the spatial S parameters, for example, might be of interest to look at developed surface area during an erosion test, or looking at the summits or peaks, these kinds of things, or a bearing analysis. These analyses are all available from this type of a technology and from the Contour Elite as well. So I hope that answers that question about what kinds of information can be provided. The traditional information about depths and widths, as well as so geometric measurements, as well as the surface texture, including ISO standard 25178 three-dimensional aerial parameters, are all available from this Contour Elite platform. Someone asked if the system can differentiate different layers of coatings or different polymers coated one on top of the other. The interesting thing is that depending on the thickness, if the polymer layers are a few microns, for example, 2 to 3 microns, the system can differentiate the signal from those. It's a capability that we have not fully implemented into the software for an automatic use, but can be easily called via a MATLAB executable that we have available. So it depends on the use case, but certainly the system can differentiate the layers and is able to make computations about the thicknesses, for example, provided the user is able to input some information about those polymer layers that are being asked about here. The indices of refraction are of great use for such a type of a computation. Someone asks about the software details. What is the principle behind for how it measures the space between 2 points to give a continuous image? So I think the question means while scanning, how is the continuous image constructed? And what is happening is, as the scan takes place, the software and the algorithms we've used to take care of the differences from a traditional microscope to an interferometric microscope, we take care of the differences in the signal, including the bias from the reference mirror that I talked about in the special objective, and also the differences in illumination to build up that continuous in-focus image as a function of the scan. Basically the peak heights on each of those are tracked while scanning, and the corresponding frames of the in-focus image are then displayed for that portion of the camera. And that's really kind of the detail behind some of the software. Someone asked, what does the software allow you to do in terms of testing? So for functional tests, and especially for engineering or engineered surfaces, primarily the system can measure step heights, volumes, dimensions of geometric features like trace widths, circular dimensions, critical dimension analysis that we have in 2 dimensions can be performed. We have a multiple region analysis which can segment the data based on height or color now, as I mentioned with the Contour Elite. The different tests that can be done then on those data can have to do with checking for pass-fail on the depth or height of a specific feature that needs to be measured, as well as surface texture. The surface texture parameters play an integral role in engineered surfaces and surfaces that are functional in nature. These can be surfaces in a dynamic sealing system, such as a ground surface of a shaft, the polymer surface of the seal, the lip seal itself, could be a clutch plate or a friction plate, brake pads, many different types of functional surfaces, could be electronic components. A lot of different types of tests can be done with this type of a system and the software. Someone asked, how effective to measure grain wear in grinding wheels? We detect grain pull-out or worn-out grains. I am not an expert on the different grain size or dimensions that would be seen on the grinding wheels. I think for sure you could measure the grinding wheel. You could try that on this type of a technology and use one of those analytical capabilities I just mentioned. The software can automatically detect the different region sizes. That would be one way to try such a test with a grain size on grinding wheel. You have to, and there it would be important to use the enhanced illumination for such a sample to make sure that you had lighting that reached down into the grinding wheel and the grain crevices, if I can imagine that type of a surface correctly. So I think it could be something to try, although I've never tried it myself. Someone asks about how does the color imaging affect resolution? This is a good question. So the resolution, again, the vertical resolution is not affected at all, and we still sample the entire array with our color imaging, although we do use a Bayer filtering technique in order to keep the speed of the scan for the color imaging. There are many ways to do this kind of color imaging. You can use multiple illuminations, alternate red, green, and blue illuminations with different scans. The Bayer filter, or Bayer filter in German, is the way that we've implemented this, and we still sample over the entire array, but use the dual green and red and blue pixel basis from the Bayer filter to do that work. Let's see, there are a couple more. Someone asks, can the system measure 0.3 millimeter down to 0.0003 millimeter, which would be 0.3 microns, so 300 nanometer up to 300 microns? Could we work as two-in-one system? And so, yes, on the order of 300 nanometers, kind of aware, that should be no problem with this kind of a technology. That's the beauty of using interferometry, even for wide fields of view, a 5x objective, which might be a few millimeters on a side in terms of the area that you image. You can get vertical resolutions on the order of 3 to 5 nanometers for vertical scanning. which should be fine to measure the range of wear that is being asked for here. A few hundred nanometer depth versus 0.3 or 300 micron kind of depth, 0.3 millimeters. I think that takes care of the list of questions, and we're about to the end of the allotted time. So again, I want to say thank you for attending this. I feel very fortunate that I got to present today after the product announcement for the Contour Elite. I changed the material slightly to go a little bit more in terms of giving an overview of that capability from the standpoint of how it can benefit for imaging, both giving the trusted metrology that we get from the 3D microscope, but then also having high fidelity images and clear results for people doing engineering tests, failure analysis tests, and these types of work. So I hope that was a clear and informative presentation. I would really appreciate it if you can take the time after you exit to spend 30 seconds and answer the survey and let us know if there are more areas of interest that you'd like to see for future webinars. And if there are questions or challenges, we can make, my email is available. The slides are presented on the web. They're published on the Bruker website, usually within a day or two. And you can get my email there and write if you have further questions, and I'd be happy to help. So I appreciate you taking time today, and thank you again, and I'll say goodbye. Thank you for your help.